Okay, last time we began with the unit 1.2 types and manufacturing methods. And we first defined some typing mistake here. But what we are looking at is, it is a planar. We are looking at as a planar. Just 1 second. Okay. So it's a planar product. What do you mean by planar product now? It is a sheet basically. It comes in roll forms. Usually the width could be of the order of 5.5 meters, very wide. In the beginning in our country, it was very, very small, but internationally, the width of 5.5 meters is quite common actually. The larger the width, the lesser will be the joints which are going to face. The other point we said is important, that it will be geosynthetics are for use in soil, rock, earth, or other geotechnical materials. And it is integral part of human-made project or man-made project structural system. I think this we amplified last time also. And we said there are basically geotextiles, and then there are subgroups in that now. The second group, main group, is geo. And having said this, these are the four main groups actually. There are so many subgroups and many others which may not strictly follow into this. So went on discussing about the first group actually, first item, which is the polymers itself, which are commonly used now. And I'm happy you recollect this issue, these points. The most common one is the polypropylene, and then we will say that polyethylene. Now, polyethylene comes in many forms. I think you must be knowing that. What is referred here is high density polyethylene, but there is also low density polyethylene, LDPE, which is commonly called as. We also have LLDPE, linear low density polyethylene. We also have VLDPE, that means very low density polyethylene. I'm sure as you keep going further now, there will be use of these things now, essentially in terms of membranes. Okay, the other common material we found is PVC is there, and then synthetic rubber, not very common these days, but it's still there. And then also we find that there are the natural fiber materials, which are jute fiber and coil fiber now. In these things, we emphasize the basic fact, though we say the polypropylene or polypropylene, whatever it is now, the resin content, that means the pure form of that material, is not necessarily 100%, it will be varying actually anywhere from 30% to 98%, though 30-40 is only referring to the PVC, but other things also, it is not 100% pure material, because we're not talking as impure, but it is actually has to have some additives to make it workable, to make it perform the functions which are going to talk as we keep going now. The other important point we tried to mention was particularly the specific gravity. The specific gravity, let us say, of HDP is 0.96, and obviously the other linear dimension will be lower than this now. Then polypropylene is 0.91, meaning thereby that both these PE and PP are obviously having a specific gravity less than water. That means they tend to float in water. And polyester, of course, has got a much heavier grammage, much heavier specific gravity. It is 1.2 to 1.38. It depends upon what is there. The other important point we also said was that the melting point is different actually. 140 degrees Celsius for polyethylene, and then 160 to 170 polypropylene, and then polyester definitely much higher than this, 250 to 290. So these will come into effect now, particularly when we are going to look at the geosynthesis required for asphalt reinforcement. Then we quickly said we didn't have a solution for that, but when once has oxygen, humidity, and some air or biological agents actually, they will actually subject this material to change. We can call it also environmental change actually, environmental degradation we can call it now. When it is of course biological, we will call it biodegradation, but otherwise it's all going to be biodegradation will be there in this now. The other important point is that after having said that this is all subject to weathering now, we should also clearly keep in mind that if you look at let us say polypropylene as a base material now, polypropylene is found to be stable by and large from around say pH 2 to pH 13. That means very heavy alkalis, very heavy acids, it is not affected. That means even in landfills, when it is going to be having high chemical strong leachates, it's not affected at all. And obviously, it's not affected by even salt water, like in sea. The other point, of course, we have to see is that polyester is equally stable, but slightly less stable than this. For example, I will put a kind of general figure of pH 3 to pH 10. That means if you talk of susceptibility to acids and alkalis now, we know that within the small range only, the small range of pH 4 to pH 10, our polyester is very stable. And beyond this, below this pH and beyond this pH also, even polypropylene and even polyethylene are quite stable. This is very general information we should think of. Okay, and then we will see how exactly we are going to treat it also. So then comes, of course, the issue of trying to make a cloth or going to make a textile, going to make a sheet. And in this now, the fundamental principle is of what we call as extruding systems. When we talk extruding systems now, we are going to use fundamentally a screwdriver system. It is nothing other than what our juice maker in a fruit shop makes it actually. We have a hopper kind of thing. Now we are going to add the polymer chips. These polymer chips are already having a mix of all these additives required at the time. And by and large, because most of these geosynthetics which are going to talk of are going to be exposed at least for some time during construction. So adding 2% carbon black is becoming very common kind of feature now. So this and any other additives required for its performance in the field are already added, mixed actually during various conditions. And then that mixture is brought here in terms of small granular form basically. So these granules are placed in the hopper, and then of course the continuous process now. And as it is coming down, actually it is heated definitely. That is, the heating elements are shown here. It is also heated continuously, and then once it becomes liquid, it is being pushed out to what we call as a spinneret or extruder. So this is of course horizontal spinning, you can see that, and here it is vertical. By and large, this is of course very common. So we find that we got this extrusion. This is a procedure which is exactly like making our bhujia or save or noodles. So that means a liquid is, viscous liquid is pushed through these small, what do you call, extruders or dies, and it out comes out the filaments continuously. So when it's coming out, the molecules we said are not orientated in given direction. They are all actually randomly oriented. So the material which is going to have in fine form, very fine form, is not having as much strength as would one wish to. And so for this, we have to go through a process. We'll see that the process is what is called orientating. What is it we are doing orientating? We are pulling along the actual direction in machine wise. Actually, by passing through rollers of different sizes now, it is being actually elongated. And this elongation is going to be giving us more and more strength. This is done, of course, under very highly patented conditions and under a different temperature and other actual conditions, environmental conditions. And so it's not something you simply pull it along it. It happens in the machine basically, and at a given temperature and a given other environmental conditions. And when once the orientation is done, only the material will have strength. That means the filament is going to have strength. Okay, so obviously this filament is circular in cross section by and large, not always, but by and large it is circular in cross section. That means like it's cylindrical in shape, like I say. And what else we do? We have to also think that even other forms of yarn making, that means even cotton yarn you make also, you always after making the yarn will actually pull along the direction. So that is called drawing. So mind you, we are using a word called orientating here because of polymeric material and sensory material. And so these molecules are, instead of being randomly oriented, are being pulled along now along the actual direction, and that gives us the increase in strength now. And then of course we said that the filaments are going to be definitely very, very fine. I will show you some of the filaments as going on. In fact, you can't see it by naked eye also. They're so fine. And that is why we defined the two terms. The very common word to describe the size, the diameter is going to be what is the weight, what is the grams actually it's going to have for a 9 kilometer long element of continuous filament. And this normally varies. Let us say 7 is very common number. 7 to 10 is the kind of dimension which we use now. Medical testers and all we may use finer one also, but for civil engineering it's going to be smaller. I mean, range is only around 7 to 10, 7 to 11 only. And when you really look at very high elongated kind of material expansion in ultra microscope now, so this is the kind of cylinder which you are going to see now, and here the filaments actually are twisted and put together. So what is that now? We had a continuous filament, and then it, of course, after drawing, after orientating and all, we try to twist it, and then of course round it up in a bobbin kind of thing, and that is what we call as a multi-filament fiber. So it is monofilament and it is multi-filament. So it's multi-filament fiber means actually it is a yarn now. So these words are textile words now. Now it's also possible for us to make this kind of, you can say yarn in a different way from what we now call as staple fiber now. What is staple fiber now? We said it is coming from the extruder or spinneret continuously. Now, when once coming continuously, we have to control this also. So, some manufacturers actually what they do, they actually, as it comes out now, they cut into small pieces now. So, pieces are usually 7 centimeter long. Okay, and then they're also, we can say crumbled basically. We'll see that actually crimped, not crumbling. It's called crimping now. So, once you are cutting to small pieces like 7 centimeters now, and then crimped, that means they are pushed in the same direction, actual direction. So, it has got, instead of a rod-like thing, it has got a wavy kind of shape now. So what exactly is happening in the wavy shape kind of shape now? This is now becoming somewhat similar to cotton. What is the difference now? The difference is that in our present system now, after staple fiber now, we have got these elements which are cut fibers of monofilament of the same diameter and the same length. And crimping also is going to give you the same kind of crimpiness now. Whereas in a natural system now, the length of the fiber is going to vary. You take cotton or jute now, the length of fiber is going to vary. It has always got a natural crimped shape, and the diameter also will vary from end to end now. So that difference is going to be there. Crimping is going to be done because once you start making the yarn out of it now, from these cut fibers, naturally that has to have natural interlocking. Otherwise, it's very smooth only. So that is why it is called crimped yarn. The other kind of thing I was mentioned is that normally all this I have shown you, the filaments are naturally like rod-like, basically, very fine rods. And that is how we extruded them now. But there is another process of getting this yarn also. This process, when we go to membranes, we will tell you. So instead of taking the extruder now, we are going to pass the same thing to hot rollers now. That means a sheet comes out. So then the sheet is again made into smaller units. We'll see the figures of that later now. And finally, when you got the finest size, actually, I will show you that sample also. It will become very thin kind of material. So that means from a big sheet, let us say of 3 to 4 meters width now, we are going to cut small length, small width pieces. The width could be maybe of the order of say 5 to 10 millimeters. And then that is actually put together, and that becomes a yarn now. That becomes a yarn, which is called as a tape yarn or slit film yarn now, because from this we make a different kind of cloth. When once come to the cloth, that means geotextile, I will show you both things also. Then another word which you use is called spun bonding. So spun bonding is a process by which up to the filament sheet geotextile, one single go actually is called spun bonding. Obviously, spun bonding is a comparison between a product which is made from a sheet film kind of thing or from staple fiber kind of thing. The spun bonded process is going to give you the best kind of material. So that process is going to give you good result. Hello?
Can you repeat? Sir, can you repeat from this unbounded, sir? Like it was done.
What is happening still now? What did we see? Just go back now. We have described the process of only extrusion, is it not? We are getting this continuous fine filament now. What are we saying now? We got a continuous filament. It's also possible for us to cut it also into 7 centimeter pieces or any other length. Usually 7 is very common. If you go to Tekka, we can see this also. And then if it is cut into pieces, it's called staple fibers now. So what is the term now? Continuous filament and staple fiber. So we can make yarn of the continuous filaments, that what we call as a multi-filament yarn now, or we can also have monofilament provided you need a larger diameter of the filament also. Okay, so both are now becoming yarn now. The other thing is now, here also I mentioned clearly that what we're having now, we are seeing a cylinder actually. It's a cylindrical shape basically, solid. It's a solid now. So as it's coming out, it's coming like a fine tube, like a fine, what we call as a... So what is happening is that it is becoming a very fine cylinder coming out now. Of course, flexible now. It's not a solid cylinder now. On the other hand, now we are going to eject actually from under this system, very similar to geomembranes, where we are going to take out thin sheets, let us say. Okay, these very thin sheets are cut into small pieces. That means they are going to split. We say when I said that the geosynthetics are usually 5.5 meter wide width now, from the polymer chips now we are going to get sheets, which we later call as membranes actually. Membranes, of course, are quite thick. They could be we can say 0.7 millimeter, 1 millimeter, or up to 2.5 millimeters, but this is very, very fine. This will be fraction of a millimeter actually. So these thin sheets basically are cut into a slit into small pieces. What are the width of the small piece now? It will be anywhere from 7 to 10 millimeters. Okay, this is put together now, and that becomes a yarn directly. So can I show you this actually? So let us say you take this now. What is this now? This looks like a synthetic robe. Are you able to see this? Hello? So this synthetic tape.
Yes, sir.
Okay, but this is not. So now, what I will do is that I will try to just open up this. Just 1 second. I will try to open up this now. So you find that it is coming out, is cut. The thin, that means is a sheet now. I cut into small pieces, small pieces, which is called slit film now. From slit film, I am putting together again and making a yarn out of it now. So this is a very different kind of thing. Actually, why it is common now? It is common for us to make a bag. I just bought a bag for you. A cement bag kind of thing now. Okay, so you see this now, in a cement bag kind of thing now, our fibers, our, what do you call, our yarns are not cylindrical. They are actually flat. You can see this also. They are all very flat in cross section. I just cut it different ways so that you can see it also. Here, of course, is very thin, and it is a flat like kind of thing. Normally in a shirting, I will show you the shirting also. It is different. So you're able to see this clearly, that this is actually slit film tape. This is a easier process. But then this process doesn't give us, obviously, high strength. That's why they are poorer material compared to what we have as a geosynthetic woven material. So you can see this, all of them are very fine. And in fact, in both directions, we'll see directions later, in both this direction, other direction of, which you call machine cross machine, the same tape is used actually. So
can you show, sir? Yeah. Can you show, yes, sir. Yes,
you can show it. This is like a cement bag, go to a construction site, you'll find cement bags like this. Go to your kitchen store, all your atta and all are stored like this only now. Okay, it is not our cloth like, it's not our shirting cloth, you find this. Okay, you see these pieces actually. You see this is very flat kind of yarn is there. Is it not? This is a tape. Basically, it looks like a tape. And so some people use as tape, or it is called also a slit film. So slit film yarn or tape yarn is a different kind of thing. It has got obviously lower strength and cheap. Why lower strength? There is no process of orientating here. Remember this now. The process is that no orientation is done in this case. Okay, so that's why it doesn't have the strength now. So because orientating is not done now, naturally the process is simpler and less expensive. That's why a new bag. Do you know what is the cost of a new cement bag? Anybody? Cost of a bag, new bag. It is hardly 7 rupees per bag, around that, depending on the size and all. If you look at used bags now, they are available for 3 rupees also. Now, what is the cost of geosynthetic now? I mean, geotextile, let us say, it will be usually some 30, 40, 25. Even manufacturing price will be very high actually, compared to the slit film tape bag kind of thing material. We'll talk of that later when we come to reinforcement. So what is that we said now? We said the slit film tape kind of thing. And in the spun bonding process, what did you do? Everything up to geotextile is made from the chips to the end product now. It's called spun bonding. It's usually done in the making of a non-woven geotextile. So let us say Type R company, that is a DuPont company, Type R product, has got that kind of product actually. That's why the best product in the world, one of the best products in the world. Okay, so denier and tex I mentioned now. Tex is a unit which we are normally going to use in terms of strength now. So we just go back, that's why I'm showing you. Okay, sometimes we also call newtons only. It's actually CN, centi-newton per denier is what you say. Centi-newton per tex is sometimes, that is another unit that people say that now. So we'll remember the textile units for this now. This is for the filament now, mind you. This is for the filament now. So we can't make much out of it from those units now, but you should remember that now. Okay, so after the extrusion now, after we got the, you can say, the yarn now, which is something like our thread only, we now start going into the manufacture of geotextiles. So geotextiles obviously are of different looks, let us say. Okay, these are all cut pieces only. So they also are black in color and not necessarily black in color. What exactly black indicates, I told you already. Black is usually color. It's not a dye. It is because it has got carbon black in this now. What is percent carbon black now? Usually 2 to 2.5% is the carbon black content. So another thing which you have to do is that in cases when it's going to expose, in cases when geosynthesis is exposed for a limited period to sunrays, it is required that it is going to be black in color. Why black in color? We expect that it will have this 2 to 2.5% carbon black in this. The carbon black has to be in a very fine form. It has to be uniform distributed or homogeneous distributed throughout the geotextile actually. Okay, so it's not that it is like a mixture wherein odd things are there. So that is, it should have not a dye, black dye. It should have the carbon black well dispersed into the material. In fact, when we are making the codes now, we are specifically mentioning, Mohan, you remember that this is a term we used also. Dispersion is very important for us, and percentage is important for us, depending on exposure. We will also see what are the other chemicals which we have to add to this now. So what are the things which we said is that from these basic elements of a polymer, from polymer we are going to draw a filament, and from filament we can also get a pieces, and then from all of them now we are going to get yarns, and from the yarns now we get a geotextile. What is the other names for geotextile used earlier? It was also called as geofabric. It was also called as engineering fabric. It is also called as filter fabric. All of them basically today we use a single word, geotextile. And if you have older books, actually older versions, you can call geofabric. There's nothing wrong with that now. But geotextile is a approved technology. Okay, ultimately it is a cloth. Okay, so what is it now? We have the same definition as we thought earlier. What is the definition now? It is a planar permeable polymeric material. And here polymeric we said it could be synthetic or natural. Okay, synthetic we mean polyethylene, polypropylene, things like this now. And then natural means something like jute and coir, textile material. Okay, planar means it's a sheet-like material. And then textile material because usually it is made by the textile process actually, which may be non-woven, woven or knitted. Mind you, another terminology is coming in now. Now we don't make a geotextile again used in contact with soil, rock, any other gel material in engineering applications and to perform certain functions. So that we'll see. So now we can think of the cloth, slit film yarn I have shown, cloth I have shown you. So this is actually a slit film cloth, slit film geotextile, obviously woven geotextile. And this is what we see as a multi-filament woven geotextile. So something like this I am showing you. So this is a multi-filament woven geotextile. Okay, and then what did we have? I can also show you actually. I already shown you the cement bag. This also is a slit film yarn made from slit film yarn. Actually, you can see this also here is a flat tape is here now. Okay, so that is another process which we are going to look at, and then by definition now it is produced by interlacing, usually at right angles, two or more sets of yarns, fibers, filaments, tapes, or other elements now. When we are trying to do interlacing is simply we call weaving only. So what is happening now? In the simplest weave now, we got one yarn in one direction, and other yarn is another direction. In this direction now. You see this now, whereas these are looks like a rod like now. Here it's bending actually between all of them now. So this simple weave actually, simplest weave. That means it is simply called as one up and one down. Okay, it is going up and then going down, going up and going down. So that's called in textile terminology, one up and one down. It is the simplest weaving we can think of. Okay, complex weave can be, it is actually one up and three down. I mean, three up and one down, something like that now. Okay, so there can be different kind of weaving which is possible now. For example, this is what I'm showing you in electron microscope view, which our own students have done at IIT Delhi actually long ago. I mean, this is taken in 1990. I still use it now. So when once you are seeing this cloth now, what is it we got now? We got this yarn now. What is the yarn we said? It is a multi-filament yarn. And you also see, particularly in this area, we also see actually small twisting is there now. Okay, and we also see this side is going to be, let's say one, and the yarn up and one down is coming in the other again. That means this is representing the simplest kind of weave. Even before we go further into this, we will also see more details now. What is this? At intersection now, it is possible to have some openings. Okay, otherwise there are no openings. There are micro openings here, but then it doesn't mean that it is sealed. It's all simply twisted together only to make a yarn now. The filaments twisted together to make a yarn. And at the intersections now, there will be definitely some small openings now. This is what we have to remember now. And then obviously we can think of having such a close packing also. That means here both the yarns are put together very closely. If it's a net-like kind of thing, they may not be so close together. So that we will see now. So what exactly is happening now? After producing the filaments now, so they are wound actually to make this. Okay. So after these tubes are made now with all that yarns now, after twisting of the yarns, and then so we come to a device which we call as a loom. Simplest loom is a flat loom. And if some of you are not going to hand loom as per any time, you should go now. So when you see this now, what is it happening now? In one direction we have what we call as a beam. Okay, in this beam, what is there really? In this beam, what is there? All these yarns coming earlier, let's show you. All these yarns coming from different points actually are all assembled together, into a what we call as warp beam. Warp is this WARP warp, is warp beam. So they are all assembled carefully, very carefully, so that they are adjacent to each other now. And the spacing is decided by a design which are making now. And you see it is in two layers now. It is not simply wound like that. It's got two layers now. So the two layers of these yarns are separated by what we call reed now. That means if reed is going up now, so let us say this top layer is going to go up. If the reed is going to be moving down, naturally the top layers are this is going to go up now. So up and down movement of these yarns is helped by the reed actually. Okay. So when once is opened up now, I can put a shuttle from this side. That's shuttle means really it is a some small bobbin kind of thing which is placed in this. I can show you that also. It is simply pushed from this direction to this direction now. And in coming out from one end to other end now, it is leaving the thread there, is leaving the what we call as the yarn now in the cross direction now. So when once that is done now, the reed goes up again or down based on this condition, and again this same shuttle is going up now. So this process was a handmade kind of thing earlier. Now it is now automatic now. We can have water jet, we can have air jet. There are many machines which are making it very fast now. But principle of this remains same only. You can see more clearly here now how reed is functioning now. The two layers of ions which are there on the beam. This is called warp beam now. And this thread which is going to go from this end to that end to the shuttle actually is now called as what do you call that now? Weft direction now. This is the warp direction. That means the direction in which the cloth is being coming out now is what we call as the machine direction from our engineering purposes now. Otherwise, because coming out from a warp beam, it's called warp direction. So warp means the machine direction. Okay? That means the strength of this in the direction is going to depend upon the number of these warp threads which are going to, or warp ions which are going to be there, and the physical number of filaments which are going to be there, the way it is brought out now. So all these threads or yarns now per unit width is going to govern the strength and behavior of this material in this direction now. What is the direction now? It is machine direction now. And then the strength and number of times is going up and down actually. That means the placement of this in this cross direction, that is what we said is weft, W-E-F-T, weft. Okay. So weft direction, or in our case now, it's called cross machine direction. What do we call direction? This is machine direction. Other direction is going to be weft direction, warp and weft now. So earlier they were counting per inch, let us say. So the ends and bits and things like that now, you don't worry on this now. We are only worried about the machine direction and the cross machine direction. If old technology of textile is there now, it is direction and weft direction now. Okay, the process is exactly going to be same. And this explains the simplest process anyway. Otherwise, there are many other processes. So you see this beam actually, in this beam now, all these yarns are really there. They are going into the system now. And from there, you can see that we can't show it because actually the shuttle is going so fast actually. So as it comes out now, that means the warp is here now. And at this point, it is moving up and down actually. The shuttle is moving up and down. Naturally, the type of material in the shuttle in the cross direction, that is the weft direction, is going to decide what is the strength and behavior of the material now. So as the material comes out, actually, it is now again wound. Okay, so we get such kind of rolls now. As I said, this roll can be 5.5 meters, not less than 5.5 meters in this case now. So another thing which you can very loosely say is that, for example, we can think of having in the machine direction, let us say polyester yarn. Okay, our direction we can also polypropylene yarn. As the machine is concerned, doesn't matter at all. Or we can have very closely spaced yarns in direction now, and not necessarily the cross direction. So it depends upon us. That means it depends on the designer now to have varying kind of materials, the raw materials within the limitations of the equipment now. So we have a number of these looms now. So like textile industry here also, for example, the scraps industry in Ahmedabad has got maybe 50 to 100 looms actually in one of the industrial areas around Hyderabad itself actually, around Ahmedabad itself. And like this now, weaving is a very simple thing. These are all what we call as sluicer looms, sluicer, S-L-U-Z-E-R, sluicer looms actually. And so this just keeps coming out. Rolls and rolls are coming. You can see how wide it is going to be. And obviously, there's no intervention. So there's an area wherein the beams are made now. Okay, and the beams are brought and placed, and then of course the weaving process starts now, and the rolling to get us a final beam. That's the factory. So that is the main thing now. So same thing we said, the warp direction and the web direction and this direction now. So the shuttle I couldn't show you earlier. So that has got this weft thread in this now. This is what is moving out of this space which is created now. So what did we say? We said this mission direction, and then the other direction is crosswind direction now. So I may just also tell advanced stage now, we have to find out the engineering properties of material in the mission direction and in the cross mission direction. Okay, that's why these are important. That means a given geotextile will have different properties on this direction, the mission direction, and the cross direction now, cross mission direction now. So that's why we define the strength or any other properties based upon. In this case, we are seeing the SCM view of woven material against geotextile. We got openings of this of different size and different uniform spacing now. So that's one thing we have to keep in mind. Then this is what I said actually is the SCM view of a slit film or tape fabric now. We see this a flat kind of thing. And also we see another important factor now. It looks like flat. The projected portion is flat now. Clear, the picture I showed you woven fabric has got projections actually at regular intervals now. Whenever the up is going to come that thread now, it is going to be upwards. But now this material, this geotextile, is now passed through hot rollers. And when once being passed through hot rollers now and bit of compressed now, what's going to happen? The projection is actually getting melted. And then this is what is happening. It became flat now. So that process called callus actually. It's going to change now. Earlier probably is higher friction, now becomes lower friction now. Okay. So we are able to see that the properties are decided by the manufacturing process. If you have a number of elements of polyester, it's likely to be stronger. If you are going to have placed very closely, all the ions actually, it's going to be probably stronger now. So if it is going to be polypropylene, it will definitely weaker compared to polyester kind of material. So this is what I said also. If you look at a typical woven geotextile, like I have shown you all these things. So another one I will show you also, wherein the strength of the material could be very, very high. If you see this now, all the filaments, so many filaments are there in this now. You can't even see them. There are hundreds and thousands of them actually in each yarn, basically. Each yarn, which is looking like this. If you just open up now, you will find that all the filaments are there. So many filaments are there. Hundreds of them are there. So they are all twisted and then it becomes a yarn now. So it is a continuous filament, multi-filament yarn. And from that is what we are seeing under microscope view of this now. So when you look at it, I try to focus your attention on the intersections now. So if you see that in higher magnification, this intersection is becoming like this. And again, you see that clearly it's triangular in this case. Now what is happening is at every intersection now, it is going to have the same kind of openings now, same size openings now. Okay, that is what you have to remember now. And now we also see, yes, there's some space, some gap also between the filaments. And here also. Okay, it doesn't mean that it's a solid kind of thing. It's not like a solid like a steel or any other aluminum or something. It is actually multi-filament fabric now, multi-filament geotextile. It will have some openings and then it also allows some water to pass through. That is very definition of geotextile. We see that now. So this is now the woven geotextile. If you look at that another kind of property, as I said now, it will have definitely strength in this direction, in the, let's say, mission direction, and then it will have strength in the cross mission direction now. So as I already said now, in the mission direction, the strength could be different compared to the cross mission direction now. It all depends upon what the number of filaments are used now, and what is the makeup of the filaments itself. Is it polypropylene or polyethylene or polyester? And then, of course, how it is woven now, what is the spacing between the yarns now. So many things are there. They will dictate the behavior, the engineering behavior tomorrow of the woven geotextile. So this of course, obviously, is a strong geotextile. What do you mean a strong geotextile? When it comes to strength, naturally, we are bothered about a unit for strength. What will unit for strength now? Normally, what is it? Strength unit basically we have?
Kilopascal.
Kilopascal. Okay. Or the newtons per millimeter square, whatever it is. Okay. That means there is a load unit, let us say, or force unit, and there is a cross-section area unit now. Now, if you want to define the strength in kilopascals of this now, yes, it's very good. Now, you also know that from your basic engineering knowledge now, that this material, its thickness now, we should know at failure. Isn't it? That's how we define the strength actually. The load divided by the unit area at failure is the strength of the material. In this case, it's very difficult for us to determine the strength of this. I mean, the thickness is so small actually. And then for this, if we are going to conduct a strength tension test now, the thickness will vary, but variation is going to be very, very difficult for us to find out, to measure. For common engineers, very difficult actually. So what is done in this case is now we define a new unit for strength of the geotextile or any geosynthetic now. What is the unit now? It is kilonewton per meter. Okay, so kilonewton per meter means we are not considering the thickness variation during loading basically. Okay, when once we talk kilonewton per meter now, so for example, the strength in direction could be say 300 kilonewton per meter. The strength in the other direction could be 100 kilonewton per meter now. That means definitely it is anisotropic from the strength viewpoint now. Okay, so that is something you have to remember. Whenever you talk of strength of a geotextile, it's always in terms of load divided by the width, unit width or unit length. That is in meters. Okay, please remember that. So then we have a blanket kind of material. So this blanket is very similar to blankets which you use for winter now. The woolen blankets, they can come in definitely different thicknesses, very thin to very thick. For example, I can show you a very thin one. Okay, and then I can also show you a very thick one. Just one second. Yeah, you can see the thickness of this. It's almost 1 centimeter thickness. So thickness is in terms of naturally what we are going to place in the material now. So again, the non-woven geotextile we are talking consisting of directionally or randomly orientated fibers, filaments or other elements, mechanically or thermally or chemically bonded now. Mind you, we got the fibers now. These fibers are put together mechanically or thermally or chemically. So then becomes a non-woven geotextile. There is no directional variation in this. We'll see that also. So now what is it we are going to have? We think of a sheet or a web or a bat. Let us see what exactly this entire thing is. We talked of two processes. We said we can make a geotextile by using this staple fiber. Let us start with staple fiber now. So we can place the staple fiber in a conveyor on a conveyor belt now. So it's very loose. And if we are going to place, so it's exactly the process of making a takia or a mattress actually by using cotton. Okay, so it's very fluffy now. So that is called a bat. Okay, or it's called a web. So this web is simply placed loosely on this now, and of course being fed from one direction now. So what is happening now in case of a stable fiber? What does it have to do? The stable fiber comes from the fiber manufacture industry in container, let us say, and those are compressed actually. So now open up all those bundles, and then a machine opens up all of them now, and then of course finally it comes as a bat or a web. Okay, so this is very loose now, and then it is now passing through a bed of needles. It's not a bed of needle really. It's two beds now. The bottom bed is actually has got holes now. There's a top bed full of these needles. Okay, so as the material is going to go on this now, on this from the bed now onto the needle bed, from the conveyor belt to the needle bed, naturally this is moving up and down. We'll see exactly. We'll come back on this again. So we'll see that these needles we are talking of are not normal needles now. So you can see this. The needle has got a projection. I mean, just showing you one element now. This was projections. So normally when you talk of stitching in a normal sense, what is happening? We got a needle. The needle is very smooth actually, very smooth, very fine. And then at the end there's a hole which is called eye, and the thread which you are going to use for stitching or for stitching your buttons or repairing your shirt, naturally it gets into the layers of textile, let us say. So the binding is happening because we made a hole and then left the thread in between continuously by some process, manually or otherwise now. So here is the reverse basically. What is reverse now? The binding is not happening because of a smooth and because of the smooth needle and the thread there. Here there is no thread at all. The needle itself is a rugged kind of needle now. You can see this projection which is there now, and there are a number of projections which are given now. So once this is getting into the geotextile, into the bat, into the loose bat now. So what is going to happen now? Naturally, it is let us say one moment, the whole thing is going to come down and go up now. So when it's going to come down now, it's going to pick up these fibers. It's going to pick up these fibers and then take it up along with it now. When once it's done now, what is happening now? This is getting compressed also. There is a mechanical bonding which is happening. So number of times it is moving now. So number of times it is penetrating. So naturally it is taking the horizontal fibers in a vertical direction now. That's why it's called mechanical bonding or needle punching. Both are same actually. Okay, mechanical bonding or needle punching. So the punching is happening. The bonding is because whatever the fibers earlier horizontal, fibers of elements are horizontal, they are now moved into vertical direction now. So it is actually kind of self-bonding now. Okay, so our tacking these together like this through this process is going to depend upon many things. How fast this is going to go up and down, what is the fastness of the movement of conveyor belt actually, and then what is the kind of needle we are going to have, what is the kind of spacing. In fact, one of my early students along with Professor Banerjee, is called Mr. Day, PK Day, Dr. PK Day, has actually produced 45 kinds of materials of polypropylene. And then he also produced another 45 or 50 of polyester. So of different denier, different spacing, many things. When time permits, we'll look into that, but not now. So the point is that we can make various varieties starting from the same kind of bed also, same kind of bat also. And then, so we can think of having needles in different, from both ends also. The spacing can vary now. You can be punching from one direction, can punch from both directions now. And this is what the tacking which is going to be done earlier. The fibers are all horizontal. Initially, they compressed by feeders, actual feeding roller now. They were loose and slowly they become thin. And out comes out actually the non-woven geotextile. Non-woven needle punch geotextile is going to come out by end of the process now. Okay. So what was happening now? The fibers which are horizontal earlier, they were actually becoming vertical now. So that is where the punching is going to help in bonding. The mechanical bonding is happening because of this system. Okay, as I will repeat, that it all depends upon the kind of needle, the spacing of that, are you punching from both directions or not now? Many things are there. There are 7 parameters which are going to do. So our student actually long ago produced so many varieties. You can relate it to my lecture given in 95. He had done the work in 1990. I think nobody else has done that kind of work in the world. Anyway, he has done all the work now. So the point is that the properties from the manufacturer. So if you want to look at the SCM view of this now, you can see this how the punching material is going to look like. So what it's got now? It has got openings of different size and different shape. That is most important for us now. Different size and different shape. That means this is what is going to make it like a filter material. Okay, what was our father Salmagas decided as a filter material? He got actually different grades of salt particles. In order that he create openings actually, which are going to allow water to get out and salt particles will be stopped from going further now. Okay, so that was, if you think of an earthen rockfill dam actually, the thickness of each of gradations could be 1 meter. And so, for example, the total filter thickness could have been in meters width actually. Here, I got these changes done just in less than 1 meter thickness of the geotextile because we are now getting directly the opening size by this now. That means by reverse method now, I have got the openings which are varying, which are different in size and shape actually. That is wonderful now. So that is what is the advantage of a blanket kind of geotextile, which is non-woven geotextile. So then the other kind of thing which you are going to see in this case is going to be thermal bonding. What is thermal bonding now? So I already shown you the bat which is going to come out now. If it is passing through again hot rollers now, it will be bonded together actually. So but that bonded together has brought out these sheets actually, which are very, very thin. And then it has got very good properties and excellent properties. So this is what we can call as a thermally bonded material. This is actually what we call as a commercially type R material. Okay, there are also other products partially thermal and one single go. So this is also another product like this now. And wherein we find that there are all continuous filaments. You can see filaments keep coming out continuously as you keep removing it actually. You can see it's a continuous filament. Okay, you can't see clearly, but the filaments is just continuous. If you think of trying to do the same thing for a material which is called as a non-woven geotextile, normal stable fiber geotextile, we find that we can't get it like this. You see, it simply breaks. After some time, it just breaks now. After since it is over now, it simply breaks. Whereas here now, it's a process which is continuous. The filaments are continuous filaments now. So it's simply coming out like that. You can't really see unless you watch carefully. So this is a continuous filament needle punch geotextile, and whereas continuous filament needle punch geotextile, it looks very similar, and you can see the holes also slightly, at least the impression you can see. And whereas the fibers which are there are discontinuous because they are all actually staple fibers now. So that is what you have to recognize between the staple fiber, geosynthetic, non-woven geotextile, and the condition filament process. Condition filament is the one which is coming out because of the spun bonding process now. And what else is left over now? That process is what is happening now. It is thermally bonded also because it's done at heat conditions. Again, you see molten actually. And you continuously advanced versions of this now. So we will once come to next unit. I will describe what exactly this is because of heat now. And then we are getting a result of so many openings of different size and different shape. Both are important. Size and shape variation is going to be very important. So that's why it will be suitable as I said, drainage and list now. So what did we say till now? We said there are two ways of making a woven geotextile. One is a weaving process, another is a needle punching process. Okay. From the needle punching, we also got into let us say thermal processing, or thermally bonded. And then there's also a process called the chemical process, wherein the entire non-woven geotextile is actually put into a resin, hot resin, taken out, as in squeezed out, it becomes a, you can say, a chemically bonded one. That is not so much in use, so I just dispensed it. So there are three kinds of non-woven geotextiles: mechanically bonded or needle punch, thermally bonded, and chemically bonded. Chemically bonded we ignore them because it actually closes all the openings which are there, so it's useless for us. So we are not going to discuss that. The other process of geotextile was actually a process which we call as now knitted geotextile. It's not a geotextile by itself. We will come back on this. It's actually it is giving a combination of a non-woven geotextile and a woven geotextile. In a way, it becomes a composite. So the compositeness is coming in because our base in this case was a non-woven geotextile, and onto this now we got these fibers, you can say, in this direction, which are say PVC, PP or polyester, or it could be glass fiber. And then this is also the same kind of thing, other direction now. And these are tagged actually by using a knitting process. So this is called a knitted geotextile. We can also call it a composite now. Now some people in presentations now, they assume that knitting is something like a sweater or something like a banyan or socks. No. Here, the yarns actually are coupled with the non-woven geotextile by using a knitting system actually. So that is why on the right side, if you see, I don't know, it's very clear or not now, but we can see up and down actually, there's a basic thread which is going to knit these yarns in position. It's actually a geocomposite basically, but because the process is knitting also, naturally, it is becoming, some people call it a knitted geotextile, but nothing like knitted geotextile. It is actually composite, geocomposite of woven and non-woven system. Okay, so we'll come back on this when you go to composites now. So what are the definitions we are thinking of? The definitions we are thinking of were a spinneret, an extruder. Is there a difference between them now? No, there's no difference between these two things. Okay, some people use spinneret. I prefer to use extruder because it makes life easier. Because spinning is a process, in textiles, it means actually getting a yarn. So I'm not looking at a yarn now. Extruder is process by which I'm getting filaments now, filaments. So filament we have seen. Filament obviously means continuous filament. Okay. And if it's not continuous in pieces now, what is it we call? We call stable fiber now. And stable fiber is not rod-like, it is crimped actually. In order to get interlocking when you make a yarn out of this. Then we have defined the denier. We defined the text. We defined the monofilament. We defined the multifilament now. So we should remember these words very carefully because we keep using them because each one of them is going to be giving us a sense of the engineering property which is going to come out of this process. That is important for us now. So I mentioned calendering. Calendering means actually passing through hot rollers now. Okay, I have shown you a tape filament fabric wherein the projections are actually molten and becomes rather flat kind of thing. So that is calendering. But then there are also processes which you may not really, at this stage, we are not doing it now. For example, I have shown the sample to you, which is a non-woven geotextile. Okay, and then elongation is very high and things like this. But then on the other side, it looks like rough actually. So what is happening now? On one side, the roller actually, that means that it's passing through two rollers now. If one roller is hot, what's going to happen now? Some of the fibers which are there on the surface are going to get molten. It got a rough surface. Okay, in the early days now of our ministry's specifications, they used to prescribe for using subgrades, for using payments now, a material which was really, we also call singeing actually, or calendaring, on which case now one side is becoming some kind of rough now, is molten, and then other side is like normal geotextile. So that is what we call as calendaring, two uses of it now. Drawing, we are not doing it in the case of synthetics now, but orientating, we are doing it now. Drawing is a process we use in fiber, natural fibers, or also for normal apparel sheets actually, or textiles. Yarn I mentioned, the filament is on. Multiple filaments are going to give us a yarn, and then naturally monofilament yarn and multifilament yarn. And then I also said the warp beam to which these yarns are wound initially. So that is giving the direction, and that is called machine direction. Other direction wherein it's going up and down actually is called left direction. It is actually called a cross machine direction, because in these two directions, which are exactly 90 degrees to each other, the properties, engine properties, are going to vary in terms of strength and elongation. So that is the view we had to keep in mind. And naturally, we go next into the next material, the geonets and geogrids now. So before we close for today, what we are going to think of is that these materials, when once they are embedded into the soil or embedded into a pavement, wherein aggregate sub base can be there at the bottom, and then before we place the base course, we place a geosynthetic, let us say, in between. So what is going to happen is, so whatever movement which is going to come out of the aggregates abutting the geotextile, that means I'm talking of a geotextile place here, and then it's placed on a sub base, and then a base course is placed. That means stones are here, aggregate is here, also aggregate is here. In between, the geotextile is there. So if there is any load which is going to come in, which is going to pull out in one direction, let us say, this direction now, what is this going to prevent now? It's going to be prevented only by the friction between the aggregate. That means between the stones which are there and the surface, again the stones which are there on the surface now. So it's only by the planar friction which is going to be coming out, but happening in both directions. Now, this is not sufficient in most cases. No. So, to have better performance, let us say, we have these kind of materials. Okay? As a beginning now, we'll see that these geonets have not been performed well. So, slowly, we'll come back to this again. We have developed what we call as geogrids now, which are stronger elements. So, that is what we'll consider in this class. Geotextile is a fabric anyway. The machinery which is used for making our own geotextiles is exactly the same thing as used for any fabric or any towel or anything else. So it's not different. So same machine is used, actually the input and machine parameters are going to be possibly different now. So yesterday I have shown you this, the other day I have shown you these pictures also, and this picture also. I think that you are very clear. So that is quite clear. This picture you have seen, the SCM view of a multi-filament woven geotextile. And we have also seen these pictures actually. So in this picture, what is it we are finding? We are finding that the fibers, the yarns from the warp beam are coming out. Now, they are not a muddled bunch of these fibers now. They are actually put in layers. You see that one layer here and the layer here now. There are thousands of these yarns actually. They are carefully wound in such a way that we can separate them into 2 or 3 or even sometimes 8 different kind of systems. Depending upon the weave actually, supposing you are thinking of this kind of weave now, it is always at only 1 up and 1 down. That means every alternate one is lifted up. Every alternate one is lifted up actually, or can be brought down. So that's why our system works basically. So what is it we have done also is that the yarn has come from spinning. In this case, it's come from spinning. What is spinning now? Any idea what is spinning? Okay, we had 2 kinds of yarns with us. One was, let us say, a multi-filament yarn. That means as the filaments are coming out, continuous filaments are coming out from the spinneret actually, we are trying to put them together and twice slightly twist it and make a multi-filament yarn. Other way, we also find exactly like in somewhat similar to cotton. Cotton has loose fibers. So our fibers are not stable fibers. So from the stable fibers also, we can spin a yarn. So that is what we're talking about, either yarn directly multifilament yarn or the spun yarn actually is put into that small rollers. They are called cone. And I have told you. So what we are trying to do is that either the multifilament yarn or the spun yarn will be having some bristles kind of thing outside. It's not so clean actually. And in the process of weaving, what is going to happen? The shuttle is going to move up and down number of times actually. So that is going to cause abrasion to the fiber, to the yarns actually. So in order that this abrasion is coming due to the shuttle and this entire reed going up and down actually, and then we are also drawing, we'll see that also what is drawing. So what is going to happen is that this is subjected to kind of strain. So for getting more strength actually, temporarily, they are sprayed with a chemical actually, something like a PVA. They are sprayed and that's how they become stronger during the manufacturing process now. That is called sizing. It's nothing to do with size actually. So maybe you can say that it is made into uniform diameter and no bristles outside protruding now. It helps in the manufacture because they will temporarily become strong because they are coated now. The other thing is that, so this reed is moving up and down actually. I mean, moving, that means bringing together the yarns actually. And, we are standing here and the warp beam is there. And slowly, as you are able to weave, that means supposing the shuttle is going inside, it went to that side by air jet or water jet actually. And so we have to draw this entire reed, we have to draw. That means we have to close up actually. So that is called drawing in this case. Earlier I told you drawing really means that we are pulling along the longitudinal direction so that it gets some strength. Okay, so that is also called drawing. Now here also they are pulled together actually in order that they become these weft yarns are coming closer and that becomes a bit stronger also. Then the weaving system comes and then inspection also is done continuously. There's somebody operator who is always watching is any break of threads and things like this now. And then ultimately it is getting rolled actually automatically. So that is the process of our making a woven fabric now. When you talk of needle punching actually, so we have the fiber. In this case, we mean the staple fiber now. The staple fiber comes to the manufacturing plant in bales. That means they are compressed together for easy transportation and they are opened up actually. And if necessary, they are blended. Of course, this refers to manufacture. For example, when can come, in the manufacture of suiting and shirting cloth actually, we can combine, let's say, polyester with the cotton or wool with some polyester or viscose. So that is what is called blending actually. We don't require blending in our case now because usually we are having the same kind of material. And then when once it's opened up actually, this opening is only initial opening only. It is really not in a very specific way. So first level of loosening that is called opening now and blending is required. And then the next process is called always carding. Carding is the process by which they linearize. That means the whole material is going through the belt actually and the rollers now. And there are needles in between such that they are linearized. That means all the what we call staple fibers are coming in one direction. That is why when I have shown you how the conveyor belt is feeding into the punching system actually, needle punching system. So I said that they are all actually more or linear and horizontal only. Okay. Now let us not imagine that all of them are just coming horizontally in the longitudinal direction as the cloth, that means machine direction. That is one way of laying them. Other way of laying is that they are not laid longitudinally, they are actually laid crisscross actually. That's called cross slapping. We'll have time to check into that now. But anyway, when once you are doing the cross slapping, that means as the machine is moving laterally, longitudinally, the material is spread on that, is being spread on that by a process of cross, we can say cross laying basically. So that means as the machine is moving now, 2-3 layers of them can come up actually. And then the punching can be done in two different stages also. One is called pre-needle loom, and then we can have finished needle loom now. It can be needled a number of times also. Okay, so that you get a thicker cloth. And then it can also be sometimes to help it to move over the conveyor belt and the punching system now. We have a material called, if you're able to see this, we have a material called scrim. We'll talk of that later also. So you can see there's a scrim actually. There's a small net kind of thing in between. It's punched together actually. It helps us in trying to see that the fibers, the staple fibers are not falling down. So that is where we have to look at it now. So a thick one is not made in one go. Number of layers can come on that now also to help the initial layer to come and not fall down anywhere on the way. And also environmental friendly kind of systems now. We have a scrim, S-C-R-I-M, scrim, which is actually a net direction different now, and the cross direction different now. That is where the cross slapping is going to give you the characteristics of winding it, and then the edges are also cut actually after winding, because edges are not perfect basically, because it's opening up and all the stitching is going on now, so they're cut, and then of course rest of it will follow. So then we have same kind of thing we can think of. Another company has produced result. There's a mixing now, opening line and mixing basin, a mixing bin, spraying the anti-static condition is very important. Anti-static coating is very important, because when tomorrow when you want to find out the grain open set distribution of that now of a nano geotextile or open geotextile, we'll have to actually also spray anti-static coating, which we'll see later now. So this anti-static coating required for geo manufacture also. Then carding, and then as I said, cross wrapping, pre-needling, finish needling, and then anything else depending upon the finish you want to give. And sometimes it is also possible for us to give a lamination to this also. LDPE can be powdered, can be done, and then it's calendared. That means when calendared means it's going through hot rollers now, so it becomes a layer now. If you really see carefully the bags which are getting now, the cement, not cement bags, the wheat bags and all, open up now, you find that outside, I told you, it is a what you call a slip film tape kind of thing, woven material, but inside there's a thin layer now sometimes. So the thin layer is LDPE or LLDPE, low density or linear low density. Polyethylene also is coated so that the material doesn't come out, the atta doesn't come out. So the good bags have got that now, and then the rest of it will follow. So there is another way looking it now. The other thing is that I told you about spun bonding. What is spun bonding now? That means right from polymer chips now, we said the fabric is going to come out in one go. So let us see that now. So we talk of extrusion, okay, and then cooling and filtering, and then spinning. That means the spinneret or the extruder is going to be coming out actually. And so all this is polymer melting. And then afterwards it's drawn. I told you the drawing process is linearizing in this case, or orientating now. And from the filament, they are laid down on the forming web. This web is very important word, because web really means it's like our blanket, it's like our razai kind of thing actually, or mattress kind of thing. That means the loose material is called a web actually. And then a bonding, we have said it is needle punching or thermal bonding, whatever is done later separately. And after that punching or any other performance, any other activity is done, then of course the fabric is made now, and then it's rolled up now. So directly, that means from studying the polymer itself now, we got all the systems now directly in one go. That is polymer melt, filament, and then web, and then fabric. That's why it is called spun bonding. So obviously in this case, it is a spun bonded automatically meant that everything is under control conditions. And also we mean that we are actually extruding it, that means through spinneret now, and already laying down actually on the forming. It's already hot actually, laid during, still not cooled, no cooling is in between. So it's laid hot actually on the conveyor belt, and again cross-lapping can be done also, or interlapping. And then what is happening is that obviously has got a continuous filament material now. That is another advantage of this now. Okay, so what is the terms we use now? For us, the spinneret and extruder are exactly the same. Filament, we said continuous filament being extruded. We defined denier, we defined text, we said monofilament, multifilament, stable fiber, and after stable fiber means cut pieces of monofilament only, and they said it's crimped actually by compressing after cutting, so that it has got that what you call crimped shape actually, and that will help interlocking when we're making the yarn out of it now. Then we use the word calendering. What was calendering? Calendering is actually passing hot rollers so that it becomes compressed also. It becomes, we can say, the outer surface can become molten, and then it is kind of bonded also. And then drawing, we said already, drawing in a weaving machine, weaving this one, or of course, it's going to be, a weaving machine is called a loom actually, very commonly. We can call machine also. And drawing also is drawing the filament so that it gets strength, the two words for that. So whatever is done in the weaving machine is called a weaving loom actually. We also call it a drafting. So I don't confuse you, but that word of drafting also is common in terms of the loom actually. Orientating word is said actually, yarn we said, and then monofilament, multifilament, spun yarn. So when you compare a multifilament yarn to spun yarn, which is one you think is going to be better now? This is made of a multiple filament put together now. Obviously, this is going to be better form of yarn than a spun yarn, which is made of a small pieces. But the process could be different anyway. The properties are different, could be varying depending upon the actual manufacturing details. Spun bonding we said now. Singeing is actually what we are trying to do. We can have hot roller on one side, or sometimes you put a flame all around, very light flame actually, so that the surface protrusions become molten, and then it gives a rough thermally bonded surface on one side actually. Okay, then we defined warp direction and weft direction. Warp direction we said longitudinal or machine direction, and this is lateral. Weft direction is lateral or cross machine direction. So these we should remember, because all our properties are going to define based upon these words actually. Okay, so we have seen the variety of these geotextiles, and thereafter we said in our major classification, in our major generic classification, we use the word geogrids only. We didn't use the word geonet actually. So here we are going to first talk about geonets, which are a precursor or forerunner to geogrids. Now, what has been found, of course, is that the geonets are of various types and shapes. We'll see that now. So what is it we observe in this is that they are obviously called nets anyway, geonets now. Now let us first see how they are manufactured. We'll come back to the definition again, but let us quickly see. So what is it we're trying to do? We're having the same polymer feed. Okay, it could be maybe polypropylene. Okay, PP. And then what is done is, we have got an extruder here now, same kind of extruder we have got here now. So earlier extruder meant that, as I said, making bhujia or save or something like that now. That means number of holes are there, apertures there, through which is pushed in molten form by the screwdriver technology. Okay. Now, in this case of making a mesh actually, a net basically, what is happening now? We got counter-rotating die. So the die is consisting of two portions now. So one, we got a ring outside, and there is a central portion now. Okay, so in this case, the central portion, the central disk, you can say, moving actually in one direction, another direction now. And it doesn't have holes all along actually. The normal extruder has got a lot of holes actually. Here, we got only a semicircular hole on this side. Let us say the semicircular hole on this side, and the other side is the holes. And then on the other hand, there is corresponding also semicircular holes on this side. So as they are moving in a different direction actually, there will be a point wherein the semicircular portion on one side and the ring, and the semicircular portion on the base plate is going to be together now. Only when they are coming together, obviously, there is a flow of the molten polymer into this now. And because they are continuously moving, these base plate and ring are continuously moving in opposite directions now, we find that they are, otherwise it was simply falling down continuously. But because they are moving in other opposite directions now, we find that there is a mesh being formed actually. And there is, of course, obviously, a molten portion which is joining intersections actually. So that is what we find. So these intersections are getting joined actually. They are going to be thick also. That all depends upon the flow characteristics and the kind of spin rate we got now. This is called counter-rotating die technique now. So as it is pushed like this now, we also have actually something like a mandrel. That means a huge, you can say a drum kind of thing now. And through which, as it's going to be moving now, this comes down and then becomes larger and larger into a tank. It's called quenching tank because it is coming out at a certain temperature, let's say anywhere between 150 to 200 degrees Celsius, and it is cooled down actually, and it is coming in the form of a cylinder now. So once it is cooled down enough now, so they are being cut actually, that's called nipping, and then it opens up. So some of you who belong to Baroda, there is also a village called Palaj actually, within about 40-50 kilometers of Baroda, actually nearer Bharuch, maybe between Bharuch and Vadodara. And you have this factory of Netlon India. The first plant established long back, that means 1970, maybe not 70, about 80 or something like that now. It still continues to produce these kind of nets now. Now, what is happening in this case is the process of orientating a drawing is missing. Okay, so we got nets like this. And we can also make by various processes different kind of nets actually. Supposing, for example, we got a net like this. Okay, and then we also got projections where you see one, we can say one strand kind of thing is coming here, another one is coming there, and there's a bonding at the center now. But in the process, there's no orientation actually. Okay, it is like this, it is like this now. And then we can also make different kind of meshes, like what we are seeing here is another kind of mesh now. Okay, it is a multiple operation also. One can have a simple net and then one can compress it, and each manufacturer makes a different kind of thing. And this kind of material was first used probably in the 70s in Japanese railways below embankments on soft soils. So what was the finding? For, of course, railway track kind of thing. So what is it they have done is they have used this now. There was interlocking of this net with the stones or soils, gravel material, and interlocking helped it to take into account the loads which are coming due to the heavy trains, quick train, fast trains. But then what they found was that these are breaking. That means these strands are breaking actually. And that means this grid was this grid shape was quite good, but then doesn't have enough strength now. So what was happening in the procedure now? We simply push them to the extruder now, automatic rotating die actually. So the no attempt is made to actually to orientate the molecules in one or two directions. So that is the main issue. And so a lot of people have tried to invent a new technology. And in that process, of course, the Tensor company produced the first kind of geogrids, which we'll talk of later, slightly to this and now. So in this terminology, we also look at what we call as BOP, which is very common, which is something like this. You can see all of them are used in packaging these days now. When you go to any super bazaar, any market, Reliance or whatever is there, you find many things are being packed into this kind of meshes actually, or nets you can say. They're all different kind of things. Not only colors now, if you really look at them, they are all made by different materials. We'll see them quickly. So before those orientated grids come out now, these BOPs are very common now. BOP really meant biaxial oriented polymers, BOP. And it's a very interesting process. What is it they have done now? They have actually used, let's say in this case, PP, polypropylene. And because of the purpose actually, in this case it's for underground coal mine, they developed this net, now we call GeoNet. And other additives are added now, and a filler is there. All of them are mixed in high-speed mixing. Then extrude is done, extruding in the same normal way. Then there is a plate calendar, and then cooling. After that now, that means they are extruding a sheet to begin with now. Okay? And calendering means they are all becoming smooth basically. Okay? And then it is tensioned in one direction, longitudinal direction, along the material, what you call, in the other direction, warp direction. And then afterwards is pulled along in the transfer direction. So we have this, what we call as bi-oriented polymer. In this case, bi-oriented polypropylene now. So after doing transfer direction now, again is cooled and then tested and whatever is there now. That is basic process. So what is it we are trying to find is that we have the initial mixture of all these materials, polymer and other additives required for the particular process. And then initial extruder is going to give you a sheet kind of thing. And then this sheet is calendared and then cooled to the required temperature. Then is punched basically. And then a process of tension is there in one direction, longitudinal direction, and then also other direction. And it shows actually that it is the transfer tension is done in two different steps. That's why it's written twice actually. Is here longitudinal tension is given in one go, let us say. Transfer is done in two goes. That means two steps now. And then afterwards it is cooled and then tested and things like this. So the machines apparently look very simple. The many machines available today in the market also. In the market means in the international market. And in fact, yesterday before I sent this original website to Mohan, I find that already people are responding by saying that, do you want to buy a new one? Do you want to buy a used one? So the machines are available now. And now I find that they are commonly used now. So we have these nets actually, which are of different kinds. The interesting point is that now there is a junction also. We'll talk of the junction later actually. So there are net kind of thing here, and there is a linear kind of member here. That means, we are able to see on the left-hand side material like this actually. Any one of you can pick up this from any super bazaar actually. These days, shopping bags all have this kind of thing also. And then you find here, like what is shown here, this is made of basically the other net, which is made of again. You can see this. This is made of individual filaments only, put together. And that's why you're able to see multiple of them now. That means in each direction now, there are two of them, three of them, depending upon how it is done actually. So by single process, we are able to produce these nets now. Okay, and for different purposes. The purpose is also highly varied. It could be obviously these days is called shade net, bird net, reproduction net now, and many things are there. And also we are able to produce actually for underground coal mine. You can see this particular net is not looking like a net now. It looks like our geogrids only. And in fact, probably is anchored actually and anchored into the sides of the coal mine, which is an entry path to the inside of the mine actually. So you find that when once it is retaining coal, obviously it's a very strong kind of net now. If it is a bird net or a shade net now, it is not going to be very strong basically. And if you think of this kind of net now, they make this kind of nets for, let's say, 1 kilo aloo or 5 kilos aloo or whatever it is now, or a big bag. And like this, we can vary the machinery, vary the things like that now. But interestingly, the most important point is that now they find that the tensile strength is maximum when the tensile ratio of the mesh is 1.8 to 1.9. 1:8 to 1:9. What exactly mean by that now? For example, in the case they have described here in one of the cases, when the punching diameter is 4 millimeters and the tensile length is 30 to 36 millimeters, the strength is maximum, which can reach 7 times when it's not stretched. The stretching means orientation now. So the improvement in strength actually will be 8 to 9 times. That is the beauty of it now. So if you think of this kind of material, if you look at your grid viewpoint now, the strength is hardly 7 kilonewton per minute now. I mean 7 kilonewton per meter actually. Whereas we're going to talk of grids and textiles of hundreds of kilonewtons or even 1,000 kilonewton per meter. So this is unoriented material. A net is unoriented, and of course, later we'll see that a grid is something oriented now. So the stretching or drawing or orientating is all going to help us in getting a strength which is of high order actually. And in this case, what is important to us? The temperature is going to be important. The speed at which you are going to put along is going to be important. It has got influence on strength, and also they follow the principle of low temperature and high speed tensile. So this is very important for us. I'll tell you why this temperature is very important for us, because it also takes a lot of energy in doing this now. And naturally, we are looking at antistatic properties also. We talk of tensile ratio and tensile speed. So we don't have to go through all these in detail, but then it will be used actually as we go further now. Interestingly, I found that even sheets, even membranes, sheet-like material also can be strengthened actually by axial orientation. Very interesting. So I thought I'd just show you. And I think you understand what is PET. What is PET? PET is PET, polyester. Polyester actually really means also called PET very commonly, or PET. It is polyethylene terephthalate. Okay. This is made of two components. One is terephthalic acid and the ethylene glycol. A combination of these two things actually gives us PET. Okay. So initially we do under some conditions now, and we produce a monomer of that PET, and then of course we produce a polymer out of that ultimately. And then either we allow that to directly come to polymerization, things like that now, and then it is being fed in the extruder, and then it is actually extruded through, again, a sheet. That means a single line notch is being done, and then it is coming out actually as a sheet now of given width now. So the point I am trying to make is now, slowly as it is going actually, it is heating, and then we are drawing forward. That means drawing forward means actually it is being elongated in one direction. The sheet is getting elongated in one direction, and obviously it is getting orientated in the direction now. And again, after that, it is cooled slightly, and then preheat to another temperature, and then again cool, because there's a process box, they will never tell us because it's all obviously IPR will be there in each one of them now. And the point is that now there is going to be now the way system is being done now, it is actually being widened. The winding only is trying to show you in the process now of all this stretching actually in the lateral direction, which they are making it as a patent issue, so they will not show that now. So here we are stretching longitudinal direction now. Here we are stretching in the, it is biaxially oriented PET sheet. It is made of spun fibers, like spun stable fibers, or it is a sheet. So in this case, the sheet itself basically is strengthened in both directions. That is important. So there are other information available now, which you don't have to mug up, but just understand now there is a temperature control in each one of them, which is obviously mixing, and then calendering, and longitudinal tension, and then transfer tension now. Okay, so the speeds are also given now. Low speed, 5 minutes for 60 RPM, speed control, this is mixing, and high speed, 5 minutes, 900 RPM, extruder mixing, extrusion, and then plate calendering, what is the speed of the rollers, and then longitudinal tension, this temperature, one stretching 10 millimeters, twice stretching 26 millimeters, and then transfers also is done. So what I am saying is that there are these which are patented now. We know the general range of things now. So any one of you can invent systems which are going to be required for a better function, for a better strength, for a better behavior now. So this gives us quickly the fundamentals of making geogrids also. That's why we have geogrids of various kinds. We'll see all of them now, but before we go to that, I forgot to show you what the definition of a geonet. It's very important for us to remember that geonet is a planar polymeric structure consisting of a regular dense network whose constituent elements are linked by knots or extrusions and whose openings are much larger than the constituents used in contact with soil, rock, and any other material, geological material in applications, civil engineering applications. So what is it which is going to be? We are talking of dense network. The elements, in this case, let us say, there is a kind of binding basically. Okay. This is coming by extrusion process itself now. Here, maybe we are doing some kind of knotting or knitting actually. So the process of linking them, we are not defining now, but the openings are much larger than the constituent. The openings, that means opening size in this case is very large compared to the size of this material which is connecting them actually, or the framework now. So that is the definition now. We are calling of a regular dense network, and nowhere we are talking of basically the engineering part of it, the strength and other things we are not going to talk of now. Okay, so that is what we call, what we defined as a geonet now, which is a forerunner for geogrids now. But more than that, we will see that how well the geonet are used, which becomes a very common component in other materials which are going to see today itself. So the next thing is geogrids, we said already. In geogrids, we find again there are a lot of materials. They all look very different, not necessarily by color, but by the way in which they look, obviously very different now. So geogrid is something which we call as a planar polymeric structure consisting of a regular open network of integrally connected, this is word is missing earlier, tensile elements, which may be linked by extrusion, bonding, or interlacing, whose openings are larger than the constituents, the rest of it is similar. So what is happening now? The open network is connected integrally by tensile elements. That is one of the most important things which you are going to see. The process can be different. Extrusion, interlacing, bonding, things are there. So we have now understood already earlier what is picture now. We had a polymer sheet. Polymer sheet usually in this case is high density polyethylene in the higher. So that sheet is taken, and then in that there are holes which are punched of given diameter, and then it's stretched in one direction. Once it's stretched in one direction now, so the holes which were circular earlier will look. So once you make like this, the material we are going to get will become like this. Okay, so this is what we call as uniaxial grid now. So the pulling actually is done in one direction. That means the orientating is done in one direction. Now you find these elements which are there. We'll describe that again carefully after a minute. So then we can also later pull it in other direction, in the lateral direction also. Once you pull it along in the machine at a given temperature, and then that gives us two element which is called as biaxial grid. Biaxial grid may look something like this. So for a beginner now, we can think that they look almost like a squarish kind of openings. Now here we have oblong kind of openings. We're not worried about that, but otherwise this is a symbol. You can say this is the uniqueness of the uniaxial grid, and this is uniqueness of the biaxial kind of grid. Okay. Now the main thing which we are going to look at is that when we try to interpose this material, let's say pavement structure, naturally the aggregate will try to get into the open here. Once you get openings now, naturally it is not able to move. It's going to constrain the aggregate pieces. It is going to interlock the aggregates. When you go to the so functions, we will describe more carefully. So the function of these openings is to interlock the base material in which is going to place now. And so this biaxial material will have more or less similar strength in both directions, both in x direction, y direction, a similar kind of strength. Whereas when we talk of uniaxial geogrid, we find that the strength is more in the longitudinal direction now. This is long direction, machine direction. So the strength is going to be more in this. And actually, in this case, you also see the thickness is varying. That means the maximum pull is here. And only the central portion is elongated. And then this portion is like a junction basically. So this is very thick, but this has got material which is not orientated now. So ultimately the strength is going to come essentially because of this orientating the molecules in the machine direction, long direction now. So this is a uniaxial grid. This is a biaxial grid now. So the Tensar Corporation, which invented this, the Netland company, which invented this in UK, has actually done extensive work throughout the world. We'll describe that as we keep going now. And this resulted in its multiple use in retaining walls, in retaining slopes, in pavements, and many applications actually. And because they did the initial research on what kind of polymer which is going to be used now, they also studied what is the kind of apertures are going to be there, the shape of them now, the process. Anyway, they were trying to invent a new process. And then, of course, they did design methodology for each one of them, and then applied the designs now, watched the performance, and brought out a wonderful book in 1985, actually, called Polymers in Civil Engineering. And that is a Bible for all of us, actually. So that is the basic material. We call them basically as a tensor geogrids. And by the very look of it, we'll actually find that they are generally very rigid kind of things. So we can also call them as a rigid kind of grid. Okay. So then we have the same thing as I've shown you, the uniaxial grid and the biaxial grid now. And we can also make them by other procedures, which are called extruded grids now. And then we have the second class of materials, which are called as woven grids actually. What are woven grids now? These are highly flexible kind of materials. We'll have a look at them as we keep going further. There are many samples of them, but I will try to skip some of them in the beginning because we are running short of time. The kind of material I said, the kind of nets which I used earlier in the first work in Japanese railways is this kind of net actually. This Netland, I think 531 or something like that now. It looks very strong, but very easily you can break it actually. If you can just put it along, it will get broken. And the kind of strength of these materials could be up to a few hundred kilonewton per meter now. So this has got 7 kilonewton. This will have hundreds of kilonewtons per meter actually. So that is the basic philosophy. And we can say, the procedure by making them also using a simple weaving technology. What weaving technology? So this looks like weaving technology. That means there's a strip here now, which is woven, and also there's another strip now. So number of strips like this, but it's coming in the weaving system. It's like a net basically. So the strips are lesser here, the strips are more here, which means that this is kind of uniaxial kind of grid. And whereas the cross variety here in the cross direction or cross motion direction now, naturally you can see them, they are very small in size. Obviously the strength is very small now, so you can say the uniaxial now. And if the both sides are similar, we can say that the biaxial kind of thing now. So this is basically on a weaving technology. You also see that they are highly flexible actually. They are like a cloth material. So we call them, because of this, a woven flexible kind of material. You grid. And earlier I have shown you the rigid ones. They are made punch and oriented also by other system which is called extruded now. So the properties of these two are similar but not same. We'll actually look into that when you go to the next session now. So we have them now. For example, if you look at going back to this now, we normally these kind of rigid kind of grids are made with high density polyethylene. Okay, and this biaxial grid is made with polypropylene. And these kind of grids are made in the country. And of course, there are many companies in India which make these woven grids anyway, both uniaxial and biaxial. So what is the definition we'll again go through? It is a planar polymeric structure consisting of a regular open network of integrally connected tensile elements. That means the tensile strength of these elements is going to be very important. The tensile strength of each of the elements becomes most important. I forgot to show you a welded grid now. So just for clarity, they made one kind of strip black in color and other direction there is white in color, but then they are welded junctions actually. So this is welded kind of geogrid made by I think one company only in the world actually. Okay, so all of them behave in a similar fashion basically. So this is the ASTM definition of it now. So after finishing what exactly we thought of the nets and grids now, what is the other thing now? It's membranes. In the membranes now, we can think of many structures which are possible. And let us quickly see what does that means. Again, we find that the membranes are of different colors, but we are not bothered about colors. We are worried about the black color, because black color means they are basically having carbon black, about 2% well dispersion system, so that they can take care of at least the ultraviolet rays effect during construction. Okay, so obviously membrane is membrane. That means it is not going to allow water to escape and even gases also. So all our carry bags we use these days now, or such kind of films, they are all membranes only. They are all membranes only. Okay. So what happens really is that they easily get punctured. You know, make hole. Just got punctured, completely broken. We stand the kind of loads which are going to be there in the field. So that's why today's membranes are much thicker actually. Okay, thickness can be usually anywhere from 0.5 to I think even 2.4 millimeters in thickness now. And apart from all these kind of materials like high density polyethylene, linear density polyethylene, and some kind of treated polypropylene, PVC, EPDM, PVC, we find that actually the thicknesses are going to be varying anyway, but most common is HDPE and PVC. And in these cases, obviously, both the PVC, of course, is preferred for water bonds and things like this. HDPE, as I said, is very highly resistant to both alkalis and acids. So we use in landfills and other applications in chemical. We can even store chemicals actually in HDPE lined ponds, basically. And it comes in width. Usually, as I told you earlier, it may come in minimum width of 5.5 meters, rarely even 10 meters, with some companies make. And they have to be seamed in the field. So that is also going to be very important, whether the membrane you make now is amenable for joining actually. The joining is usually by thermal seams. Now there are two ways in which we produce this. One, of course, the same kind of thing. We got a material which is coming from extruder actually, and then we are pushing them upward actually through a cylindrical surface now. Okay, and then we pump a lot of air into this. That means when once it's coming out actually still wet now, we are pumping air uniformly all around now. We are forming a bubble actually. So what is happening now? The air supply is coming from the center now. So it is going up like a balloon basically, and outside it is getting cooled. Okay, so this bubble is like a cylindrical bubble. You can see it actually is about 10 meter high. And then it is coming out and the nip would actually cut. That means it automatically becomes a sheet when it goes up completely. So during the process of that movement actually, material is going to be blown. This is called a blown film. And other material could be is exactly following extruder system only. So in the extruder system now, we got the same kind of thing now. And then we are going to pass through the same extruder. Extruder is going to be now a linear kind of thing now. And then, of course, we are going to nip into rolls and things like this now. So some air is required here also. So there is going to be blown film. So in this kind of system now, that is the calendering system, we have supply plastic now, and under hard conditions, it is passing through hot rollers and getting some thinning down now, and then it is compressed in further rollers now, such that it is going to become thinner and thinner to the requirement we make now. So this is definitely happening in a more controlled condition now, which makes the quality. So we can have both calendared, which is good, and also air-blown, which is good, and processes are going to vary depending upon the actual polymer we are going to use and additives which are going to be there. So this is a process of making now, which is the feed material now to make the geogrids also. The geogrids are made with this kind of membranes only to begin with. And we will also find that the same kind of material is used also making geocells actually. The raw material, the feed material for geocells and for making geogrids is of course going to be the same membranes. Now the membranes are usually used for lining, let's say, canals also. When you are using like that now, the friction between the soil and the surface, which is otherwise smooth, comes into picture. So what happens is that when one smooth now, naturally we can't place it in a steep slope actually. We have to put it a little flat now. And that is going to cause naturally issue of many things now. The space is lost and things like that now. So they could be having a smooth surface. They can be having a profiled surface like this, which is used very commonly in tunneling, or it can be textured surface. That means a rough surface is being created for this. So there are different kind of things, and the welding is very important for all of them. As a rule, thermal welding is done now. So we have three kinds of membranes now: the smooth one and a profiled one. That means projections are there, and then textured. That means roughness is there now. So these are the three kinds of things, and all of them are meant to help us in getting more friction also of the roughness. So that is the basic geomembranes now. And as I told you, there may be many raw materials which are used for this purpose. And then we come to the combination of all the materials which is thought till now. What is the combination? The combinations are going to be called as geocomposites now. Now composites again of various types. We are able to see that The types are very much varied now. Here it looks like a net now. Here is like a membrane which is rough surface now. It looks like a woven geotextile. Geotextile. It looks like different things are there here now. So these are all various kinds of geosynthetics, geocom there. So combination could be now, we can have a geonet on one side and a geotextile on one side, other side. Okay, here we got in between geonet now, on both sides we got geotextile. Here we got a membrane and a geonet put together. Here we got actually a membrane, a net and geotextile. So that is how it looks. The central portion, the net is given the symbol now, and the non-woven, this is essentially could be non-woven geotextile. So we find that this dot dot dash 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 is going to be representing this. Continuous line represents usually a membrane now. That's a symbolic arrangement notation which we are going to follow in all our drawings actually. Okay, so we can have a combination of all of them now. And by combining them now, what is happening now? We think of a geotextile, for example, a non-woven geotextile is something which is fibrous, you can say, has got a lot of openings or holes into that. It is highly compressible now. It can carry water. Probably it can work like a filter. We'll talk more about this characteristics in the next class. But then, when once water enters this area now, this becomes a spacer now. Geonet is going to be spacer for carrying more water actually. That is the purpose of this. So that is what we are going to see. So using the same principle now of combining different materials, we have a product called GCL, Geosynthetic Clay Liner now. Okay, so again it looks very different here, but let us see that GCL really means an assembled structure of geosynthetic materials and low hydraulic conductivity earth materials in the form of a manufactured sheet. So what is the low hydraulic earth material? It could be highly plastic clay, something like a black cotton soil, fine black cotton soil, or good bentonite now. Okay, so in this case now we find that there is a non-woven geotextile, under maybe woven geotextile, and then bentonite is placed in between now, and everything is punched together actually. And we can see this also. So we can initially start with a lower geotextile, maybe non-woven, it is being rolled out actually, and then through one hopper we are going to put the bentonite, and maybe the other hopper we are putting another layer now, and then we are going to unroll the upper geotextile, and in one process we can now needle it. Same needle punching could be done now, or some of the process of stitch bonding could be done. That means stitch bonding means that stitching by multiple head stitches actually, and then when once it comes out, it's going to wound up now. That is one way of manufacturing GCL. So that means we got the lower geotextile, which becomes the backing, let us say, bentonite in different layers can be placed, a different kind of bentonite can be placed, upper geotextile placed now, and needle punch or stitch bonded, and then it is wound up actually into a roll. So another kind of way could be that we start with again a non-woven geotextile could be, or a membrane, whatever, non-woven geotextile, just a membrane. Adhesive is you can say sprayed on this now. Then we have bentonite, and then again adhesive, then bentonite, another adhesive. Like that in different layers we can place now. We can place upper geotextile finally, and then of course, bentonite, it is going to become highly impermeable. Impermeability order of layers we are going to have, and the GCL is going to be basically a flexible material. And we can have different kind of GCLs depending upon the manufacturer now. Earlier we have seen this kind of thing. Now bentofix or bentomat really means that we got this needle punching done now, and the top layer can be the woven or non-woven geotextile. Base layer is a non-woven geotextile. Sometimes woven is placed as a carrier, and then bentonite, and then woven geotextile. It all depends upon the company which is making it now. We have to have performance characteristics to decide how good it is to compare to a clay liner actually. And then in this case, it's also stitched together. And a rare case, GSC gun seal company actually makes the membrane at the bottom, some kind of thin membrane, on which we are placing bentonite now in crystal form. It is actually sticking to this now. So what we are having is we got a primary layer of geotextile of geomembrane for impermeability. We are getting another layer. That means it's a double layer coming by one material called GCL itself. So this, when once it is swelling, obviously it becomes the clay liner basically, and then this is another second layer now. So there's a double layer kind of construction or composition by using this kind of GCL. So what is happening is that once you are stitching into this now, once you are needle punching into this, we already said now that the fine, you can say fibers now, are getting entangled into this now. So they are the ones which are binding this now. The needle punching is going to help in binding the entire thing. So there's kind of tacking. Multiple stitching actually is going to cause you implication like this now. So sometimes people prefer stitch bond. I mean, not stitch bonding, needle punching. This is actually stitch bonding, multiple stitches actually. And here, of course, the pieces of bentonite, which is already in pellets kind of thing, is placed, and then the suspension and other things are going to be requirement actually. And so there are many variables which are there, and usually we compare the properties of this with a geomembrane. Another kind of combination we can think of as a geocomposite, in this case called a prefabricated vertical drain, PVD, and we got a core, we got something which is surrounding this now. So that is the product is like this. We have filter sleeve on outside, center there's a core. The core I shown you earlier is simply kind of wavy shape. Different companies have got different kind of core. The purpose of the center portion is going to be take care of the water which is going to go in, and filter sleeve is to ensure that the clay, the soft clay, doesn't get into this. And we have used many such cases in India of this successfully. So the now, so the I think lakhs and lakhs of metals are used in the country, particularly Mundra, accelerate the consolidation. So that is the variety of the geocomposites you can have now. So another range of materials which is there is what we can call as geostraps, geocells, and metallic reinforcement. In this kind of cases, we'll just take 5 minutes. So in the geostraps now, what is it you find? The geostrip or geostrap, it's something like this now. It's a strip, say 10 centimeter wide. Okay. More also. These white pieces are actually polyester fibers. I forgot to mention that in the woven geogrid now, the strength comes in because they use actually polyester fibers now, whereas the rigid grids are made of HDPE and PP. In the woven geogrids now, we are using essentially the polyester fibers. So here also there's a bunch of polyester fibers now. They are put together, actually assembled together, and then they are all put together as a number of assemblies now. So more of these filaments which are going to place, it will get more strength now, how they are bundling now. There is a surfacing which are going to give it to this now. And so this is available in this kind of strip form, in a kind of roll form actually. And then naturally, this is used like our geogrid or geotextile in reinforced structures actually. So it's called geostrip or geostrap. And then we also for reinforcement use materials other than geosynthetics actually. They are comparable in performance. In fact, some of our lessons which have done, which have learned, is actually first using metallic reinforcement, and completely the uses came up actually. We'll discuss more in detail of this as we go into the reinforcement applications function now. So for developing more fiction, the projections are going to help us a lot now, and many things are there to come in with now. This is the one clip which is going to get into this to bind with the surfacing precast panel actually. So this is basically the metallic strip, which is not smooth, but then it has got some projections. So that this is one of the first patented materials which is available, and all the first reinforced structures were constructed by technology which is called as a reinforced earth concept. Reinforced earth terminology, or in French it's called terre armée, is first patented material for use in reinforced structures. And in India, we have developed, our Professor Venkataraman developed another equivalent structure wherein there's a smooth steel strip now, but there's an anchorage at the end actually, using two angle irons actually coupled together now. We developed an anchored system in this case. And world over, particularly in Japan now, such anchorages are very common now, and anchors of metal anyway. In this case, the multiple anchors could be there also. And I think the first, this kind of structures were built in Hyderabad actually, when we had this number of flyovers constructed long ago. But then they had two different things compared to this now. Instead of this anchor, which is metallic now, they use concrete blocks as an anchor. And also, instead of using a metallic strip kind of thing, they use rebars actually. Okay, so you see that now metals can be used in different shape and different form, and different anchorages can be there now. They all come under category of reinforced structures. So when we are learning the subject now, we learn how to use effectively all these kinds of materials. Then another equally challenging material, which is becoming more and more multi-purpose, is gabions. So gabions are also called as mesh boxes. Okay, and this is made of wire actually, GI wire. Now the main thing which you are going to have in this case, the boxes of course are being made by hand woven kind of meshes also, but these are actually machine made, which is called as double twisted material. You can see this twisting which is there more clearly here, double twisted. In fact, there's round off turns which is there for every kind of thing. From this, we make hollow boxes. We have to fill them with stones actually, and then we can use for multiple purposes. I mean, in fact, we require a course probably. Study itself, I got a lot of information also. And one of our research scholars at IIT have also made a major contribution to develop systems, software for designing these systems also in a automatic way. And this mesh itself can be used for reinforcement, and boxes can be used for fascia. And these are of a last kind of material as material now. What's going to happen is this can be placed, let's say, on a slope on in the river bank or in a canal also, and it's double layered. And in that we can now push in, we can pump in actually concrete or cement sand mixture. It flows over that and can get into the bed of the canal also, get to the uneven slopes on the side also. And once set now, it becomes a permanent layer, and that layer is called a geomattress actually. This will various varieties, study geonets and geogrids, membranes, geostraps, geocells, geocomposites, and of course we are left with one major component, natural fiber geotextiles. This is a subject which is different from let us say what we discussed now, but I'll just show you just 2-3 slides in trying to tell you what is the fundamental difference between these things now. We will not get you more of them, but for example, we are just comparing the material properties now. We just say jute fiber now and compare with the polyester fiber and polypropylene fiber now, filament I mean. So the tenacity is of the same order. The strength, the extension break probably is better also. We talk about the fiber. The initial modulus is also very high. In fact, that means the jute in its original form is one of the strongest materials. One thing is biodegradable. So that is the point which you have to see. The other slide I will show you, we will discuss again in more detail, is this table, wherein we discuss also the coir and the C-cell fiber, natural fiber, jute and all. So a lot of studies have been done by us in trying to compare them and trying to develop products now. So they got a good application, certain functions actually. And that, as I said, making them is a subject separate in a different way. And we will deal with it towards the end of this course actually in great detail, because these are being made exclusively in India in many different ways. So we have made a lot of strides in the country. Naturally, the organization for doing research is with the Indian Jute Industries Research Association, IGRA we call it, placed at Calcutta. Very old institution. I think since independence it is there, but of late they have spent a lot of energies in trying to develop products which are good for not only erosion control also, but for pavements actually. In a similar way, we have organizations based upon coir actually. One of them is the Central Coir Research Institute at Alappuzha in Kerala, and that does extensive work on coir material, other applications including geotextiles. So we'll deal with them in different ways as we keep going in the towards the end of the course. So we will not deal with them. But one thing which is important for us is they are no less in the virgin state. In the fresh state, they are very good. You can see the tenacity, we can see the strain, we can see the modulus now. So we see that polyester is here, viscose is here now. So we see that the tenacity, jute tenacity is very similar to polyester actually. Okay. And we also find that jute is one common way of doing it, but flax and hemp and remi, they are all hemp and remi are actually materials which are similar to jute. They come in the same family as far as we are concerned. They are available in plenty in Northeast actually. That's why a lot of focus is done on that now. So I urge you to remember all these names actually. This PPT will be shared to you very quickly. Probably before the next class, I will share it with you.